Alright, in this video I'm going to talk about the last of the three big stream-based methods, and that will be something called reduce. Now, the way reduce works is, well, we're first going to motivate this with an example. So, suppose that I want you to write the sum method that will return the sum of a list of numbers. Well, hopefully, or the sum of a list of integers, sorry, I should clarify. So hopefully, this isn't very hard. We can just do for every integer in the list, sum plus equals n, return sum. Okay? So, again, that's very simple. And, yeah, so, but let's suppose I ask you another question. Let's say I want you to compute the product of every number, every integer in a list. Well, then we would, instead of starting this off at 0, we should probably rename this to product, but like that. We'd start it off at 1 because obviously if this were 0, then we would just be having a bunch of products that are multiplied with 0. Okay? So there's that. Now, do you notice the similarity between these? What are the only differences between these two methods? Well, excluding variable names, those are not substantial differences. So the big distinctions here are what this starts off as and what operation we're applying here. And that's exactly what this is going, how we're going to motivate this method, which is called reduce. Okay? So the way reduce works is it receives two values. It receives an initial value and then something called a binary accumulation function or method. It doesn't really matter. Okay? So the initial value should probably make sense. So it's just whatever you want this to start off as. But the context behind this doesn't really quite make sense until we apply it to an example. So let's say we're summing the list of, let's say, 1, 2, 3, 4, 5. Okay? So obviously if we use the Gaussian formula, then we could just do this in one fell swoop because it's just 1 through 5. But let's assume that it's not. Like it could be 2, 4, 10, negative 68, 1000. So the reason why they're in order like that is just for the sake of the example. Okay? So if we're going to sum these, then we obviously want to start off the sum at 0, right? So the way we're going to look at this is in this funky little notation, okay? So we're going to have something that looks like a pair here, where the left thing is the current value of an accumulator, the right value is the ith value that we're looking at, okay? So when we start off the sum, of course the accumulator should start off at 0, and then we're just going to add this value to the accumulator, okay? So we get 0 plus 1 becomes 1, okay? And now this value is going to replace the existing value of the accumulator, okay? So the next time through, the accumulator will be 1, and then we'll move on to looking at this value, which is 2. And then we'll do the same thing. So we'll get 1 plus 2, which is 3. Okay? And then we'll do it again. So this value becomes the new accumulator. So we get 3 and 3. And of course, that's just because we're looking at this value now. So we do 3 plus 3, which is 6. Okay? And then we do it again. So we get 6, and then the value is 4, because we go to here. So what is 6 plus 4? That is, of course, 10. And if we do it one more time, then we get 10 and 5, which is 10 plus 5, which is 15. Okay? So the idea of reduce is that this binary accumulation function has two arguments, right? Or two parameters because it's binary, right? The first parameter is the accumulator, okay? And this is the value that changes between each iteration, so to speak, of the thing that we're traversing through. In this case, it would be a list of numbers. Okay. Then the second parameter is the value that we're looking at. Value that we're looking at. Okay. So that's just, and that changes with each and every iteration. The accumulator doesn't have to change. So that should be very clear. Like, for example, if we only wanted to sum the even numbers of a list, then we could very easily have some sort of case analysis in here to say that if the number is odd, or yeah, I actually don't remember what I said. So for the sake of the example, let's say we want to sum only the odd numbers. So we would have a case in here that says if the number is even, then don't accrue it to the accumulator, okay, or don't accumulate it. So the value is the thing that we're currently looking at, and the accumulator is the thing that potentially changes with each successive call. Okay, so notice how this would change if this were for products. Well, we'd start off the accumulator at 1, and then this would just be 1 times 1, which is 1. Okay, and then we just pass 1 here, and then put 2 here, then we get 1 times 2, which is 2. And then we get 2 and 3, so we get 2 times 3, which is 6. Okay, and then we get, we get 6 and 4, which is 24. Well, let's write it out fully. 6 times 4 is 24. And then we'd have 24 and 5, which is 24 times 5, which is 120. Okay? So the only thing that changed here is this value, and the thing that we're doing to each the only thing that changes is the initial value and the operation that we're doing. Okay? So reduce simplifies this model into a function. Okay? So reduce receives an initial value. So if we're wanting to sum the numbers, this should probably be 0. And then it receives this binary accumulation function. So to make things simple, you should probably always name the first parameter as ACC. And the second parameter can be like n or value or whatever. Okay? So this is how you make a lambda expression take multiple arguments. Okay? And in fact, we've actually been doing this notation already with the parentheses, but one thing I didn't really say was that if you just have a single, a unary lambda expression, you don't need the parentheses. They're not mandatory. But if you have more than one, then you have to have the parentheses. Okay? So yeah, so this is what the lambda expression receives, and then on the right side of the arrow, we're going to say ACC, let's do it in the same color just for consistency, ACC times, well, in the case of summing, it'd be ACC plus n. Okay? So this is how reduce would work if we were summing the list of numbers. Okay? And then for products, it would of course be 1, and then the binary operation would be the same thing, ACC and n. But on the right-hand side of the arrow, we'd have ACC times n. Okay? So let's see what this looks like in IntelliJ. So we have this list of numbers, and if we want to compute the sum of them, we can convert it to a stream, and then we're going to call dot reduce. Okay? So the first thing it receives, so it says that there's 3 different things that it can receive here, but we're going to use the one that takes in something called the identity and then the accumulation function. Okay? So let's see what that looks like. So actually, I think it's the third one that we're going to use, not the first, but it doesn't matter. So we pass in 0 because that's the thing that we want to start it off as. And then we're going to give it a binary function, a binary lambda expression, which receives 2 things, and then it will just return the sum of those. Okay? And then that's it. So ignore this yellow highlighting. This is just saying that we can replace this with something simpler, but we're not going to do that. Okay, so let's run this and see what we get. and that is 322. Okay? So let's quickly replace this with times, not division, and let's see what we get if we don't change the identity. Of course, that would be 0, because that would be the same thing as calling mul with a product of 0. Okay? So if we start off as 1, then we'll, of course, get the correct answer of multiplying all the numbers together, which, of course, is just 0, because these are zeros in the stream. But if we change those from away from zeros, then it of course gets us something that's sensible. Okay? So the cool thing about this is that we can do more things with this. So for example, let's say that we want to let's say that we want to combine map, filter, and reduce all in one. So here's what we're going to do. We're going to write some expressions. We're not going to make a method for this just because I don't see the point. We're going to write some expressions that do the following things. So the first thing is we filter out all zeros. Okay? So we keep everything that's not a zero. The second thing is we square all of the numbers. Okay? So this effectively makes everything positive, but the important thing is that I just want the numbers to be a little bit larger. The third thing is I want to convert all of the numbers into their string counterparts. Okay? So actually, let's be very careful and say integers, not numbers. And then the fourth thing is conjoin all of these strings into one. Okay? So for example, what that means is if we have like a stream of the strings A, B, C, D, E, then this would be A, B, C, D, E. Okay? So let's just go one by one. So I want to actually, how do I want to do this? Yeah, this is fine. So we'll convert this into a stream, and then, sorry about that, I had to leave the recording for a minute, but just jumping back into it. So we want to convert this into a stream, and then we want to square all the integers, so of course that's just a map operation. So we'll do map, and then we'll say the expression receives an integer n, and it's going to return n times n. Well, actually, sorry, the first thing we're going to do is the filter. Sorry, I kind of glossed over that. So we first do a filter, so receives a number n, an integer n, and we're going to keep all of the integers that do not, or that are not equal to 0. Okay, so now what? So we square all the integers, so we've done 1 and 2. Now we want to convert all of them into strings. So we can do that by another map operation. So let's do n, that's going to map to string.value of n, so that converts it into a string. We can also just do quote plus n, which will coerce this n into a string, but this is fine enough. And now we're going to conjoin all the strings into one. So of course this is going to be a reduce operation, but how exactly are we going to do that? Well, so if we're combining strings, then of course the starting value of the accumulator should probably be the empty string. And then we have the string, let's say the string A, and then this is going to return, or it's going to resolve to the empty string plus A, which then that will get used in the accumulator. So we'll say A, and then we have the string, let's say BB, that resolves to A plus BB, which is of course ABB, and then so on and so forth. So the important thing here is that the starting value is the empty string, and the it's important to realize that the order of operations here, or rather the actual operator here, is very important. So you have to use commutative and associative operations when you're working with fold or with reduce. So if you've heard of these operations called fold L and fold R, maybe from 200 or especially 211, you've definitely heard of fold R if you're coming from C211, then these are just ways of placing parentheses, so to speak, when you're doing a when you're doing a reduce operation. Okay? So let's take an example of the difference between fold L and fold R just very briefly. Okay? So if we're trying to sum up a list of numbers or a stream of numbers, then the way fold L is going to work is it's going to apply the values or the operation from this fashion. So it's going to fold it effectively from the inside out like this. Okay? So this is fold L. Fold R is actually a little bit different. So what it's going to do is it's going to say something like 1 plus, and then 2 plus, and then 3 plus, and then whatever the starting value is. So for completeness, we'll just write it all out. So we'll do 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, and then 0 for the starting value. Okay? And technically over here, this should be 0 plus 1, and then we'd have a closing parenthesis, so this should go here instead of 1. Okay? But notice that the operation will be different if the result will be different if we use a non-commutative and associative operation. For example, or a non-associative operation. Sorry, commutativity doesn't matter. So, for example, if we had, let's say, 0 minus 1, like let's say we were trying to fold over a subtraction operation. Like if all these pluses were replaced with minuses, then what would happen? Well, we can evaluate this and just see. Okay, so we'll do fold R first. So 5 minus 0 is 5. 4 minus 5 is negative 1. 3 minus negative 1 is 4. 2 minus 4 is negative 2. And then 1 minus negative 2 would be 3. Okay? So if we do fold L next, then 0 minus 1 is negative 1. Negative 1 minus 2 is negative 3. Negative 3 minus 3 is negative 6. Negative 6 minus 4 is negative 10. And then negative 10 minus 5 is negative 15. Okay? So, interestingly, the fold L operation will produce what we perceive to be the correct answer, at least for subtracting a list of numbers, or a stream of numbers, whatever, but fold R will not. Now, it's important to realize that in Java, there is no fold L and fold R explicitly. The way that reduce works is it behaves like a fold L operation, a fold left operation. But what's really important is that, I know I keep saying things that are important, but the thing that's actually kind of important here is that if you use an associative operation like plus or times or string concatenation, then fold L and fold R would be the same thing. Okay? So let's go back to IntelliJ and we'll finish this operation off. So the accumulator is going to start off with an empty string, and then we want to say that we're going to have the accumulator and then the string, and that's going to return ACC plus S, and that will be it. So reduce is a terminal operation. This forces everything to evaluate because it reduces down to a single value rather than another stream. Okay, so let's run this and see what we get. Of course, this is kind of unintelligible. So let's say we just do 0, 1, 2, 3. So this should filter out the 0 to get 1, 2, 3. Then we would get 1 times 1 and 2 times 2 and 3 times 3. So we get 1, 4, 9. And then all of these would be converted into strings. So we get 1, 4, 9. And for the sake of having multiple digit numbers, let's throw in 16 as well. So we'll say 4 is also part of this. Okay? And now we're going to combine all of these to get 1 with 4 with 9 with 16. So the result here should be 1, 4, 9, 16. And it is. Okay? So we've now worked with filter, map, and reduce. So these are the three big operations that you're going to use, particularly in problem set 4 when we talk about streams. And you'll also use these in this week's lab with streams.